and talk to you about, after you pattern resist, what you can do with that pattern resist. And in many cases, you're not just going to use the pattern resist sitting on top of that substrate. You're going to transfer a pattern into the underlying substrate. And the question was asked, why silicon? Well, silicon is nice if you're transferring that pattern into the underlying substrate, because this involves etching. The etch rate is silicon is well known. And what you're going to learn about in just a couple minutes here. And also, you can get silicon in single crystalline form. So the etch rates of silicon 100 is different than 110, and you can use that to your advantage. All right, what is etching? Well, etching. Etching is you take energy and this is the photolithography process. You saw that. And you're left with this resist sitting on top of this substrate, which in many cases is silicon. Okay, so now what you're going to do is you're going to do something to this substrate. You're going to remove it, except where the resist is. That's etching. And there's a variety of processes that you can use. You can use wet etching, and as the name implies, you're using chemicals to do that, or dry etching, where you're using ions or to bombard this surface to remove material as a result of that bombardment process. So we're going to talk briefly about that. Wet and dry etching. And there's also, underneath these, in particular wet etching, there's what's called anisotropic and isotropic. Okay, so some of that is a little alien to you, but I'll go into that so you kind of figure out what that is. Now, again, I realize we're going through this pretty quickly, and a lot of you are familiar with this, some of you are not. There's really good reference books to learn more about this if you're so inclined. And if you're going to do this, I would suggest the books by Mark Madou, M-A-R-C, Mark, M-A-D-O-U, Madou. He's written several extensive books on fabrication, both nanofabrication and microfabrication. And I think he's got the 6th edition, and though it's a series of 2 books, but it's very detailed. So if you want to learn more about this, I would refer to his books. All right, etching. Pattern transfer by chemical physical removal of material from a substrate where the pattern is defined by the protective layer, the resist. And that's exactly what Dr. Park talked to us about, is how to pattern that resist. But that's, in many cases, only an intermediate step. The next step is to transfer that pattern into this underlying substrate, which, as I pointed out, in most cases is silicon. All right, so here's exactly where Dr. Park left us. We have a film, and we have this resist sitting on top of this film. And then we're going to do something to etch this film here. And we don't want, you can actually see this right now, right? Well, if we're going to get good pattern transfer into this film, we don't want the resist to be etched, whether it's by a chemical or a physical means. If it is, that's going to give us poor pattern definition. So the etch selectivity is extremely important. It's the etch rate of the material we want to remove. That's this film here, we're removing that, you can see that here, versus the etch rate of the masking material, and that's the resist. So good selectivity, meaning we don't etch away the resist. Poor selectivity, we etch away a lot of the resist. And you can see that right here. Bad selectivity, good selectivity. Okay, that's our goal. Now, that's what we're going to try to figure out. How do we remove the underlying substrate, the film, but we don't remove the resist to get good selectivity? That's what we want to try to do. And as I alluded to, you can do that either using wet techniques or dry techniques. Wet techniques are the low technology end. You just take your resist that's patterned onto the substrate, and you put it in a chemical. The complicated, I better be careful here. The more sophisticated approach is to put it in a machine that'll actually let you remove that substrate without doing anything to the pattern resist. Gives you good selectivity in the pattern transfer process. So let's just take a look at this. The first thing I alluded to was anisotropic versus isotropic etching. So here's the resist, here's the substrate. Look what's happening here. You're getting these vertical sidewalls. So that is actually called anisotropic etching. Completely anisotropic. Vertical sidewalls, great pattern transfer. Look at this way over here. This is isotropic. And actually, as Dr. Park alluded to, you're undercutting. You're actually forming a structure here that is not a very good representation of the resist that you pattern using the photolithography process. So here's what's very cool about this. You can actually selectively choose this versus this by using either the dry etching or the wet etching techniques. Okay, so now you're sitting there thinking, who cares? What difference does it make? Oh my gosh, it's a big difference, because with the particular application, you may require vertical sidewalls that are a good representation of the resist that was patterned. It's application directed. Whereas in some cases, you may want some more hemispherical type structures and with some undercutting that you can tolerate. So this just pretty much depends upon the application. So even if you're going to have someone make your device for you, you're not going to physically do it. They're going to ask you, okay, do you want to do dry etching, wet etching? What resist do you want to use? Positive, negative? All of these are critical questions that you're going to have to share with someone before they'll make your device. All right, and you can calculate that anisotropy by using this formula up here. I won't go through that. You can go back and look at that. All right, so now we see some important things. We're going to have to understand what substrate we use. Silicon is the choice, and you'll see why in just a little bit. We have to understand what resist we're going to use, and we have to understand if we're going to use dry or wet etching, which is basically going to determine the isotropic, the anisotropic nature of the fabrication. So this is wet etching in silicon. And if you just look down here at these bottom pictures here, you're getting an idea of the different things that you can do with just wet etching. For example, all in silicon. Again, silicon is nice because you can make a masking layer by using silicon dioxide. And the etch rate of all of these chemicals into silicon is fairly well described. And if you look at here, you're using nitric acid, oxidizing agent, hydrofluoric acid, it's dissolving the silicon, and acetic acid is just a diluent here. So you mix these chemicals up, and when you have this masking layer here and this silicon that's exposed, you're going to get, is this isotropic or anisotropic? It's undercutting, it's isotropic. So nitric acid, hydrofluoric acid, acetic acid mixed up with silicon with some masking layer is going to give you isotropic etching. However, if you do potassium hydroxide, 20% potassium hydroxide, greater than 20%, at elevated temperatures, 80 to 90 degrees, look what happens. Now you're getting anisotropic etching just by simply changing the chemicals. It's still silicon, and this is silicon 110. That's the crystallographic face of that material. These are single crystalline materials in this particular case. And I hope I don't have to go through and explain that. If you're a chemist, you know what that is, but just they'll tell you what this is. But look at the etch rates. It's different. 110, 100, 111. it'll etch in potassium hydroxide at different rates to create these structures. So this is why silicon is so attractive, because of the silicon, of the single crystal nature of it, and the fact that you can select either isotropic or anisotropic etching. All right. What's the difference with glass? Dr. Vitek said, well, just you can use glass. You certainly can. It's polycrystalline. What does that mean? Well, that means that the etching is going to be isotropic, almost unilaterally, because of the simple fact that it's polycrystalline. The etch rates in silicon are defined by the different crystallographic faces of that material. And when you buy silicon wafers, you can get it as 110, 100, 111, or a mixture thereof. They'll tell you that, so you don't have to look it up. The only thing that we as fabricators need to understand is that the etch rate in potassium hydroxide, sorry about that, is different, depending upon the crystallographic face that you get. Okay. Oh, and you can see here in a single etching process with a resist patterning, you can pattern over fairly large areas, and that's pretty much determined by the mask aligner that Dr. Park showed you. It'll either do 4-inch, 6-inch, or 8-inch wafers, but you can make some pretty sophisticated structures. This thing is loaded with different types of structures. And this is just a table to show you the different chemicals that you can use here. I don't need to go through this, but just to point out, here's glass and silicon and the different wet etchants that you can use for that. Etch rate, this is a very handy little table, because the etch rate, that's what you can carefully control in all of these cases, is by just changing the time that it's exposed to the wet etchant will determine the depth of these structures. It's not really determined by the height of the resist. In this case, it's determined by how long you leave it in the etchant. So that's why if you want to make very high aspect ratio structures, the resist must not dissolve away, delaminate, or etch by the chemicals that you're using to do the wet etching. Very important to do. All right. Wow. Lots of stuff on this slide. Lots of information. And I'm going to let you go back and read about this if you're so inclined. But dry etching is different than wet etching. You're still using chemicals, I must say, but they're in a dry state. You're not dipping it in a solution that's dissolving away the substrate. Actually, it's bombarding the substrate with ions in many cases. That's actually displacing material. So that's the dry etching process. And a lot of these are characterized by physical versus chemical etching. You can see this IMB methods, and Dr. Park talked a little bit about that, versus glow discharge type methods, and all those are listed up here. So here's another thing that gets a little bit confusing, is there's not just one type of dry etching process. There's multiple types of dry etching processes. And guess what? All of them are going to give you different results for the most part. The etching rate's going to be different, the excitation power, the pressure at which you operate these systems. You can see 3 types here: plasma etching, reactive ion etching, or sputter etching. And you can, this is important if you look down here too, plasma etching, isotropic. So we now know what that means. That's going to give you poor pattern definition that's defined by the resist that's placed on top of the substrate. Reactive ion etching, directional, physical, and chemical, fairly selective. And the selectivity we know too, that's the amount of resist that's removed per unit time. The etch rate is different in the resist versus the substrate, which is typically silicon. Sputtering, it's directional too, giving great pattern transfer, low selectivity. So that's the challenge with a sputtering process. So this is just physical dry etching here. And again, as the name implies, you're not dipping this in a solution. You're actually bombarding this in the dry state in a vacuum with ions that are produced by a plasma, for example. So that's what's going on here. You can see isotropic etching in this particular case by this particular process, plasma, physical dry etching. You can see that right here. That's sputtering and ion beam milling for the physical dry etching. And this is actually showing you reactive ion etching down here. The dry etchants are different gases, carbon tetrafluoride here, SF6, and all of these, not too surprisingly, give you different results. And the main thing that's going to be different is the etch rate on silicon with using these different materials. So you can actually, if you can decipher this a little bit, reactive ion means you have ions that are reacting with the surface and carrying away material atoms. So that's what's happening here. The CF4 or SF6 is bombarding or hitting this surface. It's reacting with these ions or metal atoms on the surface and carrying them away. It's reactive. It's reacting with that substrate. And this is what's really, really nice about these type of dry etching processes is the etch rates are very well described. You can see you're removing atom by atom. So you get very great resolution in terms of the depth of the structures by the dosing time, what Dr. Park talked about, which is the power of the plasma, of the etching process, and the time that you expose the substrate with the pattern resist on it. So that's basically what's going on here in the dry etching process. Here's just showing you the chamber, and this is typically ubiquitous in many of these dry etching processes. You have an anode and a cathode, and as you suspect, ions, when they're put in an electric field, they're accelerated either towards the anode or the cathode, depending upon the charge of those ions. But in this particular case, sorry about that, in this particular case, anode, cathode, the ions are accelerated towards the cathode, and I'm removing material from this. Here's the gas that's in this plasma that's generated in this electrode configuration. So gas is coming in, the reactive gas is coming in, CF4 in this particular case, and vacuum pump to pump out those gases and removing material from that substrate. So we have an RF power source on this to actually charge this and generate these reactive ions that are being used to do that pattern transfer into that underlying substrate. This is a particularly interesting technique. You need a special machine to do what's called deep reactive ion etching, DRIE, dry. And here's the bottom line on deep reactive ion etching. As the name implies, it'll let you make very deep structures into the underlying substrate with extremely vertical sidewalls. This is, I think, and someone correct me, either Dr. Park or Murphy correct me, this is the best technique, I think, to make extremely high aspect ratio structures. Aspect ratio, the depth of the structure divided by the width. You can see that very here. It must have very good selectivity. That means it's not etching away the resist, and it's doing this with high directionality. And you can see here, it's actually, this is called the Bosch process. It's using a special technique here where they do an etching step. You can see it's SF6 here. Oh, SF4, I'm sorry, SF4 here. And it is doing some undercutting. Here's the masking layer. But what they do then is they'll etch for a certain depth, and then they'll coat this, they'll deposit a polymer on this. And what happens then is it's etching more extensively the polymer that's on the bottom of the structure, but not the sidewalls to any great extent. So that minimizes the amount of undercutting that you get after you do this deposition step. So it's a two-step process. Etch, deposit a protective layer, and then etch again. And then you go back and redeposit that protective layer. Wet versus dry etching. We've loaded into our slides a lot of tables that serve as guides for you. So if you're trying to figure out, do I want to do wet etching or dry etching? Well, you'll see this afternoon when we go through the clean room. I'm going to show you the machines that are used to do dry etching. Eeks, they're a little bit expensive and hard to operate, and they use corrosive gases. Whereas with the wet etching, you just take your substrate with the pattern resist and you just dip it in a solution. It's a little bit more easy to do, but this is pretty much predicated on the demands of what you require in your particular structure. So a lot of that is delineated on this particular slide, so you can take a look at that. And we can talk about it during our free times too. That's again what our free times are do, is to discuss some of these topics with you in more extensive detail. Yeah, I love these pictures because it's basically giving you the bottom line. What can you do with, what is the net result of making structures wet? This is etched in chromium versus dry. This is reactive ion etching. And you see, again, you get much better pattern definition for dry etching than you will get for wet etching. So just real quickly, I just need to say one more thing. I only got a couple minutes left. But putting down thin films, conductors like electrodes, electrical connectors onto chips, you got to be able to pull signals out or actuate fluid motion using electric fields. And in many cases, this requires you to put down metal films. So silicon itself is conductive. It's a semiconductor. It's partially conductive. But you can put an insulating layer on it, like silicon dioxide, SiO2. Glass is non-conductive. So you put down electrical leads, and there's several ways to do that too. You can use an etching process here. Here you have a wafer with a conductive layer on top of it. And you put a resist down, you pattern the resist, you etch using some of the techniques that I talked to you previously about. And look at, voila, you have your conductive layer pattern onto this insulating layer. Or you can do what's called a liftoff. Put the resist down onto the non-insulator or non-conductive layer, pattern the resist, evaporate metal down onto it, and then use what's called a liftoff process, where now you dissolve away, you develop the resist, and look at, you're left with this pattern conducting layer onto this insulator. You see right here, evaporate metal. How do you put metal onto an insulator or any other type of material? And there's several ways to do that. And I tell you what, we're running really short on time, so I'm just going to give you a rundown of this. We'll see a machine in the clean room that lets you do deposition, thin film deposition on insulators, and I can talk to you more about that when we're in the clean room. One is to do atomic layer deposition, and you're looking at this. You can put down very thin films of different types of metals, and that's showing you here on insulators. And you can do this with resolution in terms of lateral that's defined by the photolithography process. That's the masking layer. And with atomic layer deposition, you can put down oxides, nitrides, metals, sulfides. So you can actually put down insulators too if you want. These are, some of these are insulators here. So, these are conductors here. There's what's called physical vapor deposition techniques. I have listed here 4 of them. Let's see. Listed here, I'm going to talk a little bit about some of these. Sputter deposition, pulse laser deposition, electron beam, E-beam evaporation. We have one of those in the clean room. I'll be able to talk to you about that. And thermal evaporation. So I'll bet you every person in this room has done thermal evaporation. You take a sample, you put it in the SEM. Before you do that, you put a thin layer of conductive material over it to minimize any charging effects during the SEM. That's exactly what you're doing here. The only difference is when you put your substrate in the SEM, you don't put a masking layer on it, right? You just coat the whole thing. but you're putting down a very thin film. And that's exactly the only difference here, again, is that you have some masking layer that you can remove that defines where that conductor is going to be put down onto that substrate. And this is just giving you a picture of a sputter deposition. Again, not too surprising. It's very similar to the etching process. So you have this anode, the cathode here, which is your target. Your ions or atoms, gas atoms, are being bombarded onto this cathode. It's discharging the metal, which is being deposited on your substrate. Okay, a lot of you have seen this before. And one thing you'll notice, look at, there's no directionality. It's coming off in all directions, just like we saw for some of the sputtering processes. So here's sputter deposition, thin film profiles. Look what happens. Here's your masking layer. If you're using this sputtering process, you get some of the metal to be deposited outside of this masking layer because the non-directionality of these metal ions after they've been sputtered off the target material. This is the machine actually that we'll see in the clean room. And again, I'll be able to talk to you about that in more detail. It's pretty much the same process as that we saw here, only that we're using electron beams to sputter off the material from the target. It allows you to put on extremely and very well-defined thin films in terms of the thickness of the material. And this is just showing you some scanning electron microscope images of thermally and E-beam evaporated aluminum films. I think this is on a silicon substrate here. So you're just looking at the topographical nature of this deposition process onto these using either a thermal process or an E-beam evaporation process. All right, so I went through that pretty quick. Is there any questions? And again, I promise you during the clean room tour, we'll go back and talk a little bit more about this thin film deposition. And this gentleman here is a great expert in thin film deposition. He can give you some really good helpful pointers on thin film deposition as well. So any questions on the etching or the deposition process? Yes. Oh, yeah. The etching depth is determined by two things. It's the time that the substrate is exposed to the etch end, and also the selectivity. The selectivity, that means that the resist is not being degraded to any great extent by the etchant, right? If it's etching just as rapidly the resist as it is the underlying substrate, eventually it'll get caught up. The pattern will become distorted, and the pattern transfer suffers as a result of that. Okay, so.
So you want to know how depth?
Yeah.
So every etchant will have a etching frame. So if say you want 1 micron depth, and you should select 200 nanometer per minute etching. So if you do it for like 5 minutes, you get a 1 micron depth of substrate. That is all you select.
Yeah, and thank you, Anish. And look here. Here's all, I should have mentioned this in more detail. Here's the etch rate for these materials, wet and dry, on a particular substrate, 7 to 8 microns per minute. So that's why this table here is extremely important to provide you that information.
Based on my experience, and it just take those values as rough reference, but never trust. You have to run